So we have seen the drives in detail. We have seen the flexible drive, conventional flexible drives, modern drives we have seen. So all these rapier drives we have seen. So this and we have seen rigid conventional drives. So this we have covered, and here is what the modern rigid rapier drive. So this is what rod moving inside and outside of the shade. So how the drive, so we can see here dotted rigid rod is there and it's meshing with the pinion. So this pinion is moving clockwise and anti-clockwise. When it moves clockwise, the rapier goes inside the shade, and when it moves anti-clockwise, the rapier goes outside the shade in the telescope. Here the telescope will be there like this. So here double space will be required. So how the drive is going, see here. Here the drive comes from the main shaft here, here inside, and the bigger gear is there on the main shaft, bigger gear. To the main shaft and near to the bigger gear, two cams are there, match cams. They are attached to this bowl. Here is one bowl and backside one bowl is there. And as the match cam is rotating, this stroke cam or segment cam moves up and down. Here is what half segment drive. Here we can see this is moving forward and backward, and this will give drive to this gear. So this whole gear will be moving clockwise and anti-clockwise, and this is attached to the bevel. So perpendicular drive will come and this will move clockwise and anti-clockwise. So here from behind the big gear, two match cams are there. Here the bowl is there, two bowls, one cam attached to this one bowl, next cam attached to the next bowl. So what will happen, one time this segment, this whatever the lever is a stroke cam lever, it moves up and down. That's why segment gear moves one time up and down, and this gear will move clockwise, anti-clockwise, and here the bevel is given which moves what, clockwise, anti-clockwise. So this pinion will move clockwise and anti-clockwise. Such this is on one side of the machine. On another side, on the right hand side, such full unit will be there. So both the side the drive is given. So this is what left hand side, again right hand side, again similar photocopy or mirror image of the drive is there. So see the figure carefully. This is what flexible rapier drive. So see here, this is what screw is attached to the flywheel. The flywheel is moving clockwise and anti-clockwise, and this screw is moving clockwise and anti-clockwise. So this was from the main shaft, the drive is coming to this impeller drive. So this is going backward and forward, and the screw whatever there, it moves clockwise and anti-clockwise. The drive from main shaft is coming, and this unit is moving forward and backward, and the screw to the impeller is moving clockwise and anti-clockwise. So this schematic diagram we have seen in the backside figure. So we can see here is the figure of that screw drive. So here we can see from the main shaft, the lever is attached to the unit, and this unit is moving forward and backward, and the screw is moving clockwise and anti-clockwise. Same unit I have shown here, you can see here. Okay, so this is what flexible rapier drive. Next, in detail we will see what weft velocity curve. So weft velocity in shuttleless it is plays very important role. The velocity, as the speed of the machine increases, weft velocity of the weft increases. So velocity is important because if any weak places is there in the yarn and the weft velocity is more, and as speed of the machine increases, the breakages of the weft will be more. So weft velocity influence on weft breakage rate. So it's very important to control the velocity when the weft is going from one side to other side. So we will see how the velocity is there. So on the x-axis we are having degree of rotation, that is 0 degree, 9 degree, then front center, back center, top center, and this is what again comes at the front center, 0, 90, 180, 270. Degree of rotation of the main crankshaft here on x-axis. And on the y-axis we have shown the velocity of yarn in meters per minute. So 400 velocity, 800 velocity, 1200 velocity. Okay, so y-axis meters per minute is there. So according to the weft insertion system, we have shown the velocity curve diagram. So first we will see the shuttle loom, how the velocity is there. So one number we can see here. This is what one number figure. So at 90 degree the picking starts and 110 degree the picking takes place. So velocity of weft becomes what high when the picking or picker has strike the shuttle. The velocity of weft increases here, and in the shade the velocity remains constant. Okay, it is near about 900 meters per minute, and when the shuttle reaches to opposite shuttle box, the swell mechanism is there to reduce the speed of the shuttle, so weft velocity get reduced, and again the shuttle strikes to the what picker, and your complete shuttle will come at zero position, zero velocity, and rest position at 270 degree. So this is what the curve of shuttle loom of weft velocity, behavior of weft velocity in shuttle picking system. So this is what one. Second, see here Sulzer loom. So here is the second one. So here is the second curve we can see here. It is like this. Here is like this. Here they like this. So see here what happens at 100 degree twisting of torsion rod will be there and release of torsion rod will be there. As the release of torsion rod is there, the picking shoe hits the projectile and the projectile velocity increases suddenly. At 100 degree, 110 degree, it reaches to the near about 600 meters per minute, and this speed is maintained in the shade constant, and as the projectile comes to the other side, the projectile braking is there and suddenly brings the projectile to the zero speed. Not like shuttle, first the swell mechanism will reduce the speed and the shuttle will come to rest. Here it is not like that. The projectile will break the projectile. The quick braking will be there, and here complete resting of projectile and zero velocity it goes. So this is what weft velocity of projectile machine. Third is a rapier loom, Deva system. Deva system means what? Left hand side rapier will take the weft from the picking side and it brings to the center of the machine, and the next rapier from the right hand side picks the weft from the left hand side rapier and delivers it to the right side of the machine, that is called receiving side of the machine. So these are what giver and taker rapiers. So we can see here the velocity is not simple harmonic motion but non-simple harmonic motion. So we can see here this is what curve to mountains, okay, and below 800 meters per minute speed is there, 800 meters per minute. So see here how it is behaving here. As the weft is gripped here, the velocity increases and as the weft reaches to the center of machine, the rapier becomes slow here. As it goes to initial, the rapiers run fast, and next as it start reaching the center of machine, the speed of the rapier reduces, the speed of the weft reduces. And here the weft is gripped by the right hand rapier. The right hand rapier grips the weft, and as the rapier goes back, the velocity of the rapier increases, the velocity of weft increases, and as the rapier reaches the right hand side, the receiving side, the velocity of weft reduces. So here we can see the unique characteristics of tip to tip transfer Deva's type of rapier weft insertion system. So this is what weft velocity pattern of the Deva's type. Next is what fourth one is what Gabler type. In the Gabler type, hairpin system is formed, and the hairpin, half hairpin system is formed in the width of machine, and half side of the peak is straightened by the right hand rapier. By the left hand rapier, the hairpin system is formed, and by the right hand rapier, that hairpin is what straightened. So here we can see this is what fourth curve. At 100 degree, left hand rapier brings the weft to the center of the machine. So velocity increases suddenly up to fourth point. And here the right hand grips the weft and straighten it. As it starts straightening, the velocity of the weft drops. So this is not the velocity curve like Deva system. This is what Gabler system it is. Next we can see fifth is water jet. Water jet means what? The weft is inserted with the friction of water. So there is a friction of water particles and weft. As more is the friction between your weft and water particles, more the distance the weft will fly and with the higher velocity. So here we can see by the water pressure the weft is going here. So fifth we can see here. And near about 140 degree the picking is there. 100 degree the pick is inserted, and in the shade. This is what the weft is going in the shade completely. Here also in the Gabler system the pick is going half of the shade. In the next half we have straightened it. But here the picking is inserted at 140 degree and 140, 50, 60 degree. Within 20 degree the weft goes to the what receiving side. Within short span of time the weft goes to the what next side. As the next side the weft goes, the velocity get reduces because water jetting forces reduces. So here picking starts for few degrees, and then picking bombarding of water particles is what 0. That's why here the weft velocity get reduces. So this is what weft velocity curve of the water jet. Next is what circular loom. Circular loom is what multi-phase loom. Here more than one shade is formed and more than one peak is inserted at a time. So more is the production than the what single phase loom. So see here, this is what sixth. See here what is the thing we can see here. Here hardly we are having what 50 meters per minute speed, and the speed is what constant throughout the rotation of the crankshaft. So this is what very interesting curve, and here we have completed what 6 looms where weft velocity pattern is different. First one is what shuttle loom, second loom is what projectile loom, then third curve is what Deva's type of rapier, fourth is what Gabler type of rapier, fifth type is what water jet, and sixth is what multi-phase loom, that is what circular loom. So see the weft velocity curve. If any problem is there, you can chat on the chat box. So draw the figure. Will give 2 minutes for you to draw this figure. So here we can see effect of read width on the loom speed. This is what read width. So minimum width is 120 centimeter, 200 medium, 250 medium, and maximum is 380 centimeter read width. Read width means what? From left hand to right hand, the width of the read on the machine. So this is what increasing order of the read width we can see here. And here is the A scale. That is what? Picks per minute. So picks per minute is nothing but what? RPM of the machine. So from 0 RPM to 100 RPM, 200 RPM, 300 RPM. RPM is nothing but revolutions per minute is nothing but picks per minute. So there is no difference between RPM and picks per minute. 100 revolutions per minute means 100 picks you are inserting in 1 minute. So here we can see here 0 to 100, 200, 300. These are what? RPM and picks per minute. Next is B. B is what here? Rate of weft insertion. So rate of weft insertion 300, 400, 500, 600. So 300 weft meters per minute means what? Or 600 meters per minute means what? So 600 meters of weft we are inserting in 1 minute. So this is what? Weft insertion, rate of weft insertion rate. Weft insertion, that is called as WIR, weft insertion rate. So this is what? First is what? RPM of the machine, second is what? WIR, and third is cost, capital cost per kilometer of weft inserted. So cost of production to insert 1 kilometer of weft. So this is what? C on the C. So we will see the effect of read width on this RPM, effect of read width on the weft insertion rate, and effect of read width on the cost of production of the weft. So what will be the cost to insert 1 kilometer? So effect of width on these three things we will see, A, B and C, as the width of the fabric increases or width of the reed increases. So see here what is happening here. First we'll concentrate on the A. So we can see here as the reed width is increasing from 120 to 200, 250, 380, the A curve is falling down. Means what? A means what? Picks per minute is falling down, means RPM of the machine get reduced, revolutions per minute get reduced at the width of the machine increases. So how it is possible? As the width increases, there will be more time to required to insert the web from one side to other side. Means what? It takes more time to insert one pick from one side to other side. More time for picking is required as the width of the machine increases. So that's why the speed of machine get reduced. So similar is seen here. As the width of the fabric increases, the RPM reduces or picks per minute reduces. Picks per minute means what? As the width increases, the machine reduces the speed and amount of weft insertion per minute, that is picks per minute. So as the width increases, picks per minute reduces. So more the more the width, less number of picks will be inserted in 1 minute, and less the width, more number of picks will be inserted per minute, or RPM of machine will be more. Here RPM of machine will be less, that is what? Picks per minute insertion will be what? Less. So this is what our A curve. Next is what? B. Here from here, as the width of the machine increases, B goes on increasing. So B goes on means what? Weft insertion rate, rate of weft insertion in meters per minute. So how much weft we can insert in 1 minute? So at this point we can insert 350 meter per minute in 1 minute. So B point means what? Here we can insert at the B 500 meters per minute at 380 centimeter width of the fabric. So as the width increases, weft insertion rate per minute goes on increasing. So we know that how to calculate the weft insertion rate now. So weft insertion rate is equal to width of the fabric into speed of the machine. So once again you write down weft insertion rate in meters per minute is equal to width of the fabric into RPM of machine. So here we can see the curve. Here the speed is falling or picks per minute is falling, and here the what is increasing? Weft insertion rate is increasing as the width of fabric increases or reed width goes on increasing. Next we will see capital cost per kilometer of weft inserted. So how much it costs to insert 1 kilometer of weft as the reed width increases. So as the reed width increases, the C curve we can see it is going down, again it is increases. So slightly goes down and again it increases. So 0 to C here, this is what x axis for this, and this is what y axis. So we can see here the cost goes somewhat less at the center, again it increases. So there is no change in cost per kilometer for smaller width or wider width fabric. There is no effect on the cost per kilometer of weft inserts. So we have seen A, B, C effect on the what? Reed width. So take some 2 minutes to draw this figure. So next again we'll do some revision on weft insertion. So in the first figure, second figure and third figure, the clearly difference of the single rapier, double rapier, Tevas and Gabler system will be there. So we'll revise what we learned in the what classification, drives and weft velocity curve. So see here, so first position is what single rapier loom. So weft package is on the opposite side and the rapier insert from this side, and here the weft is ready. This is what width of the fabric. First figure it is ready. So second figure here is the got clamp. Weft is ready in the clamp. So here what happens while going the rapier goes empty throughout the width of the machine. It catches the weft and brings to the what receiving side. So this is what picking side, and this is what receiving side. So single rapier is going from only from the one side to other side. While going it is going empty, while coming it brings the weft. So it is what single sided rapier. Packages on the other side. So sample loom in our workshop is of the single sided rapier. In the next figure, we can see this is what Deva's type of system. So here left hand rapier, right hand rapier, and this is what the width of the fabric. Here the gripper is there, weft is ready here. So here what happens, as the right hand rapier enters inside the shade, it grips the weft and brings the weft up to the what center of the machine now. And here this rapier from the opposite side comes empty, and here the exchange of weft is there, and this carries the weft back, and this goes what empty. So this rapier goes empty here, and this carries the weft from the center. So this is called as what tip to tip transfer, or it is called as what Deva system. So this is what double rapier Deva system. Double rapier Deva's system. Next we can see double rapier cabbler type of system. Means what, here we are forming hairpin. So here this is what the width of the fabric, and here is what left hand rapier and right hand rapier. So right hand rapier or the giver makes the hairpin up to the center of the machine. So we see here we have got the hairpin here. Here is the gripper. So this like this hairpin is formed, and as the opposite side left hand rapier grips the weft and it starts going back. Here the grip, here the clamp leaves the weft, and this half portion, topward half portion, is straightened by this opposite rapier. So this is what straightened. So hairpin is what here straightened by the left hand side rapier. So again here the bit up will takes place, and again next cycle starts here. Again hairpin is formed here by this right hand rapier up to the center, and this hairpin is straightened here. So two picks we have shown here. So this is what hairpin system, double sided rapier, gabler type of system. So we are clear what is single rapier, where it is double rapier, that is what Devas, and gabler. So draw the figure to clear your concept. So here we can see clearly this is what left hand rapier, flexible rapier, on which the left hand rapier head is attached. So this is called as also gripper. This part gripper is attached, left hand gripper, to grip the weft from the left side. And this is what right hand rapier, and this is what flexible tape on the right hand rapier. And this is what sleigh. On the sleeve we can see here guides are there. So in the guides the rapier tip is going inside and outside. So this is what guided rapier. You can see a guided rapier, and this is what left hand rapier. So design of the rapier we can see, this is what giver and taker. So giver and taker design we can see here. At the center they collide with each other. Taker rapier goes inside the giver and grabs the weft at the center and brings to the what right hand side. So we have seen there is a disadvantage in the guided rapier. We cannot have more EPI. If the more EPI is there during opening and closing, the warp abrades these teeth and chances of warp breakages are there. And same, more EPI fabric we cannot run, and also what will happen, more fancy yarn in the warp we cannot run. due to increase in the breakages. But nowadays the guided rapiers are not there. The guided rapiers are removed, guides are removed, and the tape width has been increased. So see the sleigh here, aluminum type of sleigh. So very less width is there, and weight is there. As the weight is less energy is required for beat up, forward and backward moment beat up. Here the reed attachment will be there at the screw. So forward and moment is very less energy is required. That's why the speed of the machine can be increased. This is what the added advantage. So we will stop here. In the next lecture we will start the features of flexible rapier.